So very good evening to all. This is and welcome to the live discussion session, live problem solving session for sixth for the course entitled Basic Thermodynamics, Classical and Statistical Approaches. This course has course code NOC24 CY04, and myself Akash Gutal. I am a PhD student from Department of Chemistry, Indian Institute of Technology, Jodhpur. So in today's session, first we will revise whatever the content that we covered last week in NPTEL lectures. And last week, I think we have solved some tutorial problems. No particular topic has been covered. So let's revise certain formulas which are important in today's session to solve problems. So the uh, we know that the entropy, we have defined and learned about entropy, and we know the second law of thermodynamics, which is related to the entropy, which says that entropy of the universe always increases for spontaneous process. So the entropy of universe will always increase when the process happening is spontaneous. And if it is a reversible process, then the entropy change will be zero, the universe. And this leads to the second law of thermodynamics statement, which is delta S of change in entropy of the system plus change in entropy of surroundings is always greater than or equal to zero. So this uh, always greater than zero there for the spontaneous process. And if the process is reversible, then it will be uh, the change in entropy will be zero. So after that, uh, we require the expression for the entropy when the body is maintained at constant temperature T, means the isothermal process. The entropy change is nothing but the reversible work done, isothermal, reversible work done, which is nothing but uh, equal to T delta S, right? which is nothing but the heat uh, gained by the system. And for the body transforming from temperature T1 to T2, the heat, the entropy dq by T is nothing but Cp into dt by T integrated from 1 to T1 to T2, which in turn give you Cp ln T2 by, and for n number of moles it will be ncp ln T2 by T. Let me introduce one another slide. Fine. So there is one more important relation between entropy and the volume of the gas, which can be given as delta S is equal to nR ln V2 by V1 for system changing volume from V1 to V2. So entropy change can be given as delta S is equal to nR ln V2 by V1. This is also important relation we need to take. So entropy is actually proportional to natural log of volume. This is the important outcome that we get from this equation. So, we will move towards some problems. We will solve some sample problems related to these equations. So the question number one is the efficiency of an engine working between two reservoirs, T1 and T2, where T1 is greater than T2 is 1 minus T2 by T1. It is true for all engine, true only for Carnot engine, and the given formula is wrong and none of the above. So you can solve. I will give you some time to solve this problem. Take 2-3 minutes. Simple. You can solve. So the efficiency of the engine working between two reservoirs. T1 and T2 are reservoirs where T1 is greater than T2. formula is given as eta is equal to 1 minus T2 by T1. So whatever the temperature is less is given in numerator. So we need to determine which statement is true from given four options. So here we are having T1 is greater than T2, and our efficiency will come out to be 1 minus T2 by T1. As this is true, then your eta value will always less than 1, which is which does not break any law. So this is true for every engine. So eta must be the efficiency must be less than 1. Efficiency 1 is not possible. So efficiency uh, can be less than 1 for any engine, not for Carnot engine. Carnot engine is having maximum efficiency possible. But for all engine, it is true that this value must be less than 1. So the formula is not wrong. So the cold temperature is at, because of this value is coming less than 1, as T2 is less than T1. That's why eta will be less than 1, which is true for all engines. So your answer must be, the statement is true for all engines. Nothing wrong with it. Fine. So we will revise the efficiency also. So efficiency can be given as work done divided by heat supplied to the engine. Fine. And it also can be given as, suppose there is a system where we are having engine E. If it is doing some work W, it is taking heat from heat reservoir, hot reservoir, heat QH, and it is giving to the cold reservoir QC with TC, then your efficiency will be your work done divided by QH, the heat given to the system. Work done is nothing but the difference between heat supplied to taken from hot reservoir minus heat supplied from cold reservoir, heat supplied to cold reservoir divided by heat taken from hot reservoir, which is nothing but 1 minus QC by QH. And as we know, QC by QH is actually proportional to TC by TH, which will give you 1 minus TC by TH. So we know these two formulas. Fine. This is the first question. The second question uh, is a cool body at temperature T1 is brought in contact with high temperature reservoir at temperature T2. Body comes in equilibrium with reservoir at constant pressure. It's given. And considering heat capacity of body C, show that the entropy change of universe can be given as. The four options are given. You need to choose right. Please try on your pen paper. Just try to solve this problem. So I'm giving you the 4 minutes to solve this problem. If you want to know answer, you can forward this uh, recording and check how uh, I'm solving this problem. And if you want more time, you can stop this recording and do your calculation, but do by yourself. So there is one body, a cool body, which is having temperature T1, and we bringing it with the contact with high temperature reservoir. It is a reservoir with temperature T2, and it's a reservoir. Means reservoir is something which maintains that temperature. It is a temperature T2, then it will maintains that T2 temperature. Whatever you heat add, heat get from it, then even if you take out the heat from it, it will maintain its temperature to T2. So that's called reservoir. It's having infinite number of infinite heat is there inside this reservoir, and it is having only temperature T2. And the T1 will comes with in equilibrium with this T2 temperature, and at constant pressure is considering heat capacity, that Cp, the heat capacity is C. We need to find out entropy change of the universe. We need to find out entropy change of the universe. Fine. So we are having body. Sorry for that. We are having body T1 and we are keeping it in contact with, so we are having a body, fine. We are having a body T1, T1 at temperature T1, which is cold. We are keeping it contact with a reservoir. So this is a reservoir with temperature T2. Fine. This is T1. And what happens after time? Equilibrium will happen, and this T1 will become T2. So this cold body temperature will become equal to the reservoir temperature T. So what is happening? The heat flow, according to second law of thermodynamics, heat flow will happen from hotter body to colder body. So that is happening, which means it's a spontaneous process. Spontaneous process is happening. It will be flow from reservoir to your cold body, and after equilibrium is achieved, then both the temperature will become same. As it is as this second body is reservoir, it will maintain its temperature at T2. Whatever heat you it take out from it. So change. So what we can say, we will be having uh, there are three entropy changes, two entropy changes, which is entropy change for uh, entropy change for colder body, and entropy change for, we can say, the system, entropy change for reservoir. Let's say entropy change for cold body, just body, and this entropy change for reservoir, and we need to find out entropy change of universe. Fine. So first we calculate entropy change of your body, which is changing its temperature T1 to T2, which can be given as, so this will be your, it's a forming Cp, that will be Cp into dt by T, integrating from T1 to T2, because the T1 temperature is increasing and to form T2 spontaneous. So for that spontaneous change, we having equation Cp integration T1 to T2 dt by T. So that will give us, the Cp is nothing but the C into natural log divided by T2 by T1. So this will be change in entropy of the cold body. For the reservoir, which is maintain its temperature T2, but heat taken from the reservoir, as we can see, C into T2 minus T1. This heat is actually taken from the reservoir. As it is taken from the reservoir, we will put negative sign and divided by the it reservoir is maintaining its temperature constant T2. The entropy will be minus C into T2 minus T1, which is nothing but the dq, and dq by T is the definition of the delta S, that is the entropy. So what we are getting here, delta S body and reservoir entropies. So what we know, uh, that we can write this as C T1 minus T2 divided by, right? So whatever the entropy of universe is nothing but change in entropy of a body plus change in entropy of reservoir, which is nothing but C T1 minus T2. Let's put the reservoir first, 2 plus C ln T2 by T1. So we are what we are getting, C into T1 minus T2 divided by T2 plus ln T2 by T1. Let's match with the options that we are having. So option number 1, if you can see, T1 minus T2 divided by T2 plus ln T1 by T2. You just check the numerator denominator in natural log. Here we see T2 by T1 is there and the sign is plus. But if you check, everywhere we are having T1 by T2. If you write this thing in T1 by T2 form, it will be having C into T1 minus T2 divided by T2 minus ln T1 by T2. So this will be our delta S universe. And that is option number, if you find, option number 4. Fine. Okay. Next question. The correct expression for entropy is, 4 options are given: del Q reversible by T, del Q by D. T, both A and B is correct depending on the process. None of them. Take 2-3 minutes to understand the question and just answer uh, if possible. So the correct expression for entropy is del Q by del Q reversible by T, del Q by T, both A and B is correct depending on the process. None of the above. So entropy is defined by the change in entropy is defined by change in heat at reversible manners with constant divided by the temperature. This is a standard and definition of entropy. So we can say the reversible heat absorbed by reversible heat absorbed or released anything absorbed by by a system per unit temperature. So this is the definition of entropy. Fine. That's why correct answer is option number A. The next question, question number 4. What is the thermal efficiency of heating? You have to find out what is the thermal efficiency. Diagram is given. Draw this diagram in your notebook. Try to understand what process are happening. It is cyclic process. As we can see, the system is coming at the same point. When it is happening, cyclic process is there. We are asked about the efficiency of it. Please do calculate. Take your own time. So we are asked about the thermal efficiency. First, read the diagram. We will read the diagram. What processes are happening. So if you see, suppose let's give the names to the process or the points. This is point A, point B, point C. And as you can see, A to B, we are having process in which the expansion is happening, but the pressure and volume are not, nothing is constant. Both are variable. And the second is A to B processes, A to B process. We don't know, but the P and V both are not constant. These are variable. And the process B to C, B to C, we can see it's isochoric process. Isochoric process in which the volume is constant, the pressure is varying, and the process A C to A is C to A is isobaric process. And Q is entering in from the only one process. It is given from AB. Q is taking inside, and that is QH. Fine. QH is getting inside. So if we are given a PV diagram and and the process is cyclic or PV diagram is given, and you asked about what is the work done by this process, then generally the work done is the area under the curve, or the area that this cycle covers is nothing but the work done. It's nothing but the work done by the system. Fine. So we can easily calculate what is the work done. So we have a triangle which is having its height. This is its height, and this is its base. So what is the height? Height is nothing but 40,000 minus 20,000 is nothing but 20,000 Pascal. And the base is B is equal to 0.2 minus 0.1, 0.1 meter cube. Fine. And we need to calculate what is the area forming by this triangle. Which is nothing but the area, which is nothing but the work done by the cyclic processes, 1/2 base into height. The base is 0.1, the height is 20,000 Pascal meter cube. All unit is Pascal meter. So this will give us 10,000 into zero point 0.1, nothing but the 1,000 joule. This is the work done. So Pascal meter cube is standard SI unit. Right? And we have the Q. So we have a Q. So we can write Q as Sorry, my pen is not working. 2 minutes. So yeah, it's working. So Q that we are having is, let me, okay, I will continue from here. So Q that we are having is Q is equal to 4000 joule, and W is we having 1000 joule. So we need to find out the efficiency. Efficiency is nothing but the work done divided by heat taken from hot reservoir, which gives rise to 1000 divided by 4000, which is 1 by 4, which in turn gives you, I think, 0.25. The answer should be here. It's 0.25. Fine. This is the answer. So the next question. What if anything is wrong with this refrigerator? It violates the second law of thermodynamics. It violates the third law of thermodynamics. It violates the first law of thermodynamics. Nothing is wrong. Please think about it and try to solve it. Take 4 to 5 minutes. So the hot is a refrigerator. It's taking 40 joule from cold reservoirs and is giving 30 joule to the hot reservoir. 10 joule is work done on the system. we are asked to check out whether it is breaking any law or violating any law. So in this problem, we can see, let's check whether it is, uh, let's check by calculating the coefficient of performance. Beta is nothing but the QC, the heat taken from cold reservoir, divided by work done in, or we can say on the system or on the refrigerator. So work done is can be defined as QH, sorry, QH minus QC. Okay. So coefficient of performance will be QC divided by QH minus QC. That will give you, if you calculate this coefficient of performance beta, we'll get QC is 40 joules, QH minus QC, QH is 30 minus 40. And if you find this, this will get out to be minus 10, which is the minus 4. The answer, the beta will is minus 4. But we know that beta must be greater than 1. Must be greater than 1. So beta for any refrigerator is actually greater than 1. And the ideal refrigerator, it is 1. But that refrigerator never possible. It's the same as that of the uh, heat engine, which is the heat engine with having efficiency 1. It's not possible. The same way, uh, the beta value, in the same way, uh, the refrigerator with efficiency infinity, sorry, the coefficient of performance tending to infinity is not possible. So beta never tends to infinity. And the beta value, it must be greater than 1. When it is less than 1, we can say it is violating something which is related to energy. The conservation of energy is violating. That's if it is less than 1. Because whatever you input, putting the work into the system, and we are getting the energy 40 joule from the cold reservoir, it should transfer 50 joule to hot reservoir in order to uh, fulfill the first law of thermodynamics, but which is not happening here. Hence, it's violating the first law of thermodynamics, the conservation of energy, and its beta value is coming negative. So that's why this given system is violates the first law of thermodynamics. So this is not possible. Beta tends to infinity. I will write in different way. Beta coefficient of performance tends to infinity, and eta tends to 1. It is never possible. Fine. The next question. Rank in order from largest to smallest the work W performed by these four heat engines. So four heat engines are given. They're TH and TL. The TH means T hotter and hot, and T lower temperature is given. You need to compare their work done. Let's take 4 minutes to solve this question. And if possible, tell me the answer. So here we need to calculate the work. If you find, so it's simple because we know the QH, the heat taken from the hotter body and heat given to the cold QC, and we know the definition of the work done is QH minus QC. That simple it is. Just subtract 100 minus 60, which is nothing but 40 joule, 200 minus 160, which is nothing 40 joule. For third heat engine, 90 minus 60, which is nothing but 30 joule. And for fourth system, 90 minus 40 is nothing but the 50 joule. So what we have, the work order is the highest work done will be done by the fourth engine. Then we will having the first, and first is equal to the second because the third 40 is the same. And then the lowest work done is by third number. And this option is option number two. Fine. The next question. We'll move towards next question. Uh, okay. Seventh question we will do later. Question number eight. Three reversible engines of Carnot type are operating in series as shown between the limiting temperatures of 1100 K and 300 K. Determine the intermediate temperatures of the work output from engines is in proportion of 3 to 2 to 1. So in this question, the heat engines are operating between the two temperatures T1 and T2. T hot is hotter temperature is 1100 Kelvin. That's 1100 Kelvin, and the colder temperature is 300 Kelvin. And three consecutive heat engines are actually operating in between these two temperatures. And their work output is given as 3 to 2 to 1. The ratio is 3 to 2. Proportionally is 3 to 2 to 1. And we need to find out what are the two intermediate temperatures that are there between these three operating engines, heat engines. So please take 5 minutes to solve this question. It's a little lengthy. You need to do more paperwork for this. Please do. Small hint is that you can uh, rather doing the extensive algebra once you got the functional form between these two relation between these two temperature, you can put the options that are given in this question. We can put directly this option and we can verify the answer, and you can find it quickly rather than solving the entire algebra. So we'll solve this question. So we'll first draw the diagram according to the information given in this question. So sorry, this is the hot reservoir TH, which is having 1100 K, and we are having here cold reservoirs, let's say TC of 300 K, and we have three heat engines that are operating in between these two temperature, three heat engines, E1, E2, and E3. So this is the heat taken, which is Q, let's say. So providing heat output to the second engine as they are attached in series. And the work is done by the each engine. We having here the work done by each engine. And we know their relation. The work is done by the first engine, let's say 3W. The second engine is 2W, and the first engine is 1W, which gives you the same proportion as 3:1. And the heat taken from the by the first engine, that is QH, is nothing but, let's say it is Q. Rather than writing it's QH, we will say it is Q. So for that, charge. So Q is the heat taken from the hot reservoir, and E1 engine will transfer heat to the E2 engine. What will be that amount is nothing but Q minus the work done 3W. And the same way, E2 will transfer the heat from E2 to E3. That heat will be transferred as 3 minus 3W minus 2W. Fine. And which is nothing but Q minus 5W. And heat at the end, E3 will dissipate heat to the cold reservoir Q minus 5W minus W, which is nothing but Q minus 6W. Fine. So how we're going to approach this problem is, let's find out their efficiencies. So we're having two formulas for efficiencies. The first formula is efficiency is equal to work done divided by heat taken from the hot reservoir. And the second formula is 1 minus T hot, sorry, T cold divided by temperature of hot reservoir. Fine. We are going to use these two formulas. And the first we know that, so let's write these three efficiency formulas for the three equation. We will be having three etas. The first eta will be which we can write as, let's write in terms of temperature first. Eta 1 is equal to, so we will write it in new slide. Let me add one slide. Wait, fine. So eta 1 will be, we are having eta 1 is, let's say we will give, let's say the temperature of in between this hypothetical reservoir is T1 or E1 to E2, T, let's say T1 2, and for this is T2 3, fine. Or for our convenience, let's say it's T1 and T2, fine. That will be better. So eta in terms of temperature, we can write 1 minus for first engine. For first engine, it is TH, T1 divided by TH. Sorry. So T1 we don't know, and TH we know that it is 1100 Kelvin. So this is by eta 1. Eta 2, similarly, we can write. Let's write it in terms of eta 2 is the T1 is its hotter temperature, and T2 will be the cold temperature. So 1 minus T2 by T1 will be the efficiency of E2. And for E3, the similar way, T2 by TC, T2 and TC, it's operating between T2 and TC, and its efficiency we can say is 1 minus TC, which is nothing but 300 Kelvin, divided by T1, T2 is its water temperature. Fine. Similarly, we can write in similar way etas in terms of work. We can write work and heat. So the work will be W. Work done by first engine is 3W, as we know, and its heat absorption will be the Q. Yeah, Q. Similarly, eta 2, heat, its work done is nothing but 2W, and as we know, so that as we know, it's it's uh it's heat taken from hot reservoir. Its hypothetical hot reservoir is Q minus 3W. Similarly, for eta 3, it's single W divided by Q minus 5W. And these are the three equations in terms of work done and heat absorbed. So if you see, we can take out, we have W and Q are constant here. Constant in the sense, we can write this eta 1, eta 2, eta 3 in terms of W and Q. Let's write this three equation in terms of W by Q. So in the first equation, N1 is equal to 3W by Q, which W by Q or Q by W. Anyway, so we will be having uh, 1 by Q by W is equal to nothing but 3 by eta 1. Fine. This is our first equation. The second will be N2. Eta 2 we are having. Eta 2 is 2W by Q minus 3W. We can divide by W, and we will be having 2 divided by Q by W minus 3. And if we rearrange it, by rearranging, we will get QW is equal to 2 plus 3 eta 2 divided by eta 2. Fine. Q plus 2 plus 3 eta 2 by eta 2. And similar way, we are having third relation, eta 3 is equal to what we are having is eta 3 is W by Q minus 5W. Again, Q minus 5W. We divided by W, we will get eta 3 is equal to 1 by Q by W minus 5W. Similarly, if you calculate Q by W, by rearranging, uh, we'll be having mm, 1 plus 5 eta 3 divided by eta 3. So we are getting three different equations for three different. So what is the common in all three equations is Q by W. So because of that, we can equate this to these three temperatures similar way. If you find the ratio of their efficiencies, so it will be 3 by eta 1 is equal to 2 plus 3 eta 2 divided by eta 2 is equal to 1 plus 5 eta 3 by eta. Fine. But we are having information. So these three equations are three relations are having three different variables, eta 1, eta 2, eta 3. But already we know their relation previously that eta 1, eta 2, eta 3 are actually depend upon only two variables, which is T1 and T2. So we can reduce this system, this equation or this proportionality in terms of T1 and T2. So we will put the eta 1, respect to eta 1, eta 2, eta 3 values so that we can get the relation between T1 and T2. From that, we can calculate what is the T1 and T2. So for that, we just put this three equation in our current proportionality equation. 3 by eta 1, which we will, I will start in this thing in new slide. I'll take the new slide for that. Yeah. So we'll be having this 3 by 1100 minus T1 divided by 1100 is equal to Q plus 3. And what we are having is here T2 by T1, T1 minus T2 by T1. So this will be T1 minus T2 by T1 divided by eta 2 means T1 minus T2 by T2. I think it is T1 minus T2 by, sorry. T1 minus T2 by T2. One second. It's T1 minus T2 by T2. So T1 and T2 is okay. So, yeah, it is right. Fine. This is T1 minus T2 by T1 because the T1 is hotter temperature for the uh, T1 is actually, as you can see, it's hotter temperature for engine heat. So the equation must be 1 minus T2 by T1, which is nothing but T1 minus T2 by T1. And we will be having the third thing is 1 plus 5 into T2 minus 300 divided by T2 and divided by same thing T2 minus 300 divided by T2. Fine. So if we directly do the algebra 1100 minus T1 divided by 11. If you take it upside, then this will be 3300. Once we multiply by 3, and this will be T1 into Q divided by T1 minus T2. Okay. And if you divide it, then it's plus 3, which nothing but which we can say for this thing also we can say it's T2 by T2 minus 300 uh, plus 5. Fine. Then let's simplify again. D300 by 1100 is T1. Let's take only two equations. I think it's Q is coming here. And no, something is not where I'm getting this Q. No, it's not possible. It must be 1 plus 2 plus. It's not 2. It's not Q. It's 2. Sorry. Right. It's 2. Yeah. 2 into T1. It's 2 into T1. So if you can see, these two equations are simple. We will take these two equation relation T2 by 2 minus 300 plus 5. First, we take the equation between the two, and available option we can put. Uh, let's put T1. T1 is 730. If you put a 700 T1, let's check T1 is equal to 700 and T2 is equal to 30. If you put 700, then LHS will be 700 minus uh, uh, divided by and 1100 minus 700 is nothing but 8.25. Okay, this is LHS 8.25. Let's calculate RHS for 30. T2 is equal to 30. 30 divided by 30 minus 300 plus 5. So 30 divided by 30 minus 300 plus 5 is 4.88, which is wrong. So LHS is not equal to RHS. For second option, T1 is equal to 700, T2 is equal to 400, 430, 33.3, 433.3. We will be having LHS is equal to 8.25. RHS is nothing but 433.33 divided by 433.33 minus 300 plus 1. It's coming out to be 8.25 exactly. Fine. So LHS is equal to RHS. We are having, hence our option must be T1 is 700 and T2 must be 433.3. So the option answer must be option number B. So the next question is, during the free expansion, 2 kg air expands from 1 meter cube to 10 meter cube volume in an isolated vessel. Determine entropy change of the universe. So take 2-3 minutes to solve this question. Give me the answer. So expansion, three expansions in them, and the 2 kg of air is expanded from 1 meter cube to 10 meter cube volume in isolated vessel. Remind the entropy change. We need to find out the what is the entropy change of this system. So I will actually there is one input is required in this particular problem is 20. We I will define the molar mass of air is as 28.97, right? Exactly, gram. Fine. Take molar mass of air as 28.97 gram. Calculate. So we know the formula. We'll solve this question. Let's take out the given. The mass of air is given as 2 kg. We'll calculate the moles. The number of moles are 2000 gram divided by 28.97 gram. Stress rise to this is nothing but 2000 divided by 28.97 is giving out to be 69.036 or 37. Right? And V1 is given 1 meter cube. V2 is given 10 meter cube. Expansion is happening. And we know the formula change in entropy is equal to NR ln V2 by V1. We asked about the entropy change of the universe. Fine. So system plus surrounding, we know entropy change and systems entropy plus uh, surrounding is entropy. Surrounding entropy here is 0. The system entropy will calculate n R ln V2 by V1 and nothing but the entire universe's entropy change. NR ln V2 by V1 is, as we can see, is N is 69.037 cross 8.314 joule into ln V2 by V1 is 10 by 1 ln 10. Calculate it 69.037 cross 8.314 cross ln 10 is giving rise to, that's the answer, 1321.6231 joule per Kelvin. That's the delta S of system. And we know delta S universe is equal to delta S system plus delta S surrounding. So here delta S system is nothing but 1321.6231 joule per Kelvin plus the surrounding entropy. If the free expansion is happening, no heat is lost or gained. So the surrounding entropy change will be 0. And delta S universe is nothing but the value we are having here, option number B. Fine. So thank you very much for attending the session. So today's session I am concluding. We'll meet next week, Tuesday, 7 to 9. Thank you very much.